Hi, and welcome to Virtual Class 13. Today is Thursday, May 14th. Three quick items that I want to mention before we get started today. Our next lab on thermochemistry is scheduled for May 21st. This is a really fun lab. I really wish we were in the building to do it, but we're going to go over that next week. Second point that I want to make is that our next exam, our last exam, is scheduled for Wednesday, June 3rd. And then today we're going to continue on our thermochemistry unit by talking about enthalpy. So stay tuned for some fun stuff. Alrighty. So to begin today, we're going to talk about enthalpy. Enthalpy is simply the amount of energy released or absorbed as heat during a chemical reaction. Now, we use two terms to talk about energy being heat energy being released or absorbed a few class periods ago. So those terms were endothermic and exothermic. So what I wanted to do is now assign a value, so positive or negative, to those two terms. So as you can see, the delta H is what we're going to use to describe enthalpy. So that's the variable that we're going to use. And when we have a positive value for delta H, that means that we have an endothermic reaction. That means heat is being absorbed as a result of the chemical reaction. Now, we'll see this later when we look at some reactions, but heat being absorbed means heat gets written on the left side of the equation. Now, if we have an exothermic reaction, a reaction where energy is being released, notice that delta H carries a negative sign, and that energy would be written as a product on the right side of the equation. There are two other terms that we're going to talk about, and those are entropy and free energy. So let's look at entropy first. This is a weird one, right? Entropy is a measure of the randomness or the disorder of a system. So if you think about disorder, what are some of the things that are most disordered? Well, I'll tell you, gases. Gases are completely random. Their molecules are moving all around in the container in a completely random motion. So if you want to think about something that's highly disordered, think about a gas. Now, on the opposite end of that, if you want to think about the thing that is most ordered, you're going to think about a solid, right? The molecules are in fixed, rigid positions. They're not really moving around at all. So if you think of something that's highly organized, think about a crystalline solid, like a chunk of sodium chloride. So if we were to organize all phases of matter in terms of randomness, we would actually start off with the lowest being a solid. Then we would actually move up to a liquid of that same material. Then we would move into an aqueous solution, because an aqueous solution has two different components to it. That's a little bit more disorganized. And then finally, the most disorganized would be our gas, way at the top. So if you look at the two terms, we have a delta S. So if a delta S is positive, that means disorder is increasing. It's becoming less organized and more random. And if you have a delta S that is negative, that means disorder is decreasing. It's actually becoming more organized. So moving closer toward either a solid phase or something that is less organized than a gas. And then finally, let's take a look at our last term, which is called free energy. So free energy is the energy available for work, the energy in a system that's available to carry out work. And really what it is a way of determining whether or not a reaction occurs spontaneously or non-spontaneously, meaning it doesn't occur. So if you look at the variable that we use for this, we use delta G, and a positive value for a delta G means that the reaction does not occur, it is non-spontaneous, and a negative value for delta G means that the reaction does occur, it occurs spontaneously. So if I mix two things together, this reaction will occur. Now, free energy and spontaneity does not incorporate rate of reaction. So you can have a reaction that occurs spontaneously, but might take 100 years to happen. So spontaneity just talks about whether the reaction will occur without any outside influence. Now, you can get non-spontaneous reactions to occur by basically adding in enough energy to make it spontaneous or to make it occur. So free energy, really is talking about whether or not a reaction occurs. A negative value means that reaction is spontaneous. A positive value means that reaction is non-spontaneous. So what we're going to do next is we're going to kind of combine all three of these terms together and try and figure out when a reaction would actually occur based on enthalpy and entropy values, and when a reaction would not occur based on enthalpy and entropy values. So to do that, I'm going to send it out to our resident staff scientist, Kevin, who's going to kind of put all these pieces together. Take it away, Kevin. Thanks, Kevin. All right. So in our next segment, what I wanted to do was to relate these three different variables that we just heard about to each other. So first we have delta G. Delta G, remember, talks about whether a reaction is spontaneous or non-spontaneous. Does it occur or does it not occur? Delta H talks about heat energy, and a negative value for delta H means the reaction is exothermic. Heat is leaving the reaction, it's being given off. Or delta H is positive, it's endothermic. Reaction is needed in order for, energy is needed in order for that reaction to occur. And then finally, we're going to look at our last variable up here, which is delta S. It is a measure of the disorder, how disorganized the system is. Remember that disorder, high disorder is something like a gas, and low disorder is something like a solid. So reactions tend to want to move towards more disorder, just like your room. You know, if you forget to clean up after yourself after like a week, you have clothes all over the place, that's an increasing disorder. That's the natural tendency. So for a reaction to occur spontaneously, there's usually an increase in disorder. It becomes more disorganized. All right, let's take a look at the combinations of these two. So according to our equation up here, if you have a reaction that is exothermic, meaning this part is negative, and you have an increase in disorder, meaning this part is positive, the result is that delta G is going to be negative 100% of the time. So what we're going to write it over in this box is always spontaneous. This is the best situation that you can come up with for a reaction to occur. So you have a release of heat energy, meaning it's moving to a lower energy state, and you have an increase in disorder. Now, if I jump down to the opposite of that, this is like your worst case scenario. So if you have a reaction that is endothermic, meaning you have to put in heat energy for it to occur, and it's decreasing disorder, it's becoming more organized, think about how unlikely that is to happen. You're adding heat to something, and that something is going to move toward forming a solid. That's very unlikely. So these reactions are always non-spontaneous. Then you have that gray area in the middle. So when you have a combination of a negative and a negative, or a positive and a positive, the possibility for delta G is either positive or negative, and it depends on a few things. So if you notice, for this first situation where we have an exothermic reaction, so delta H is going to be negative, if it decreases in disorder, that means it becomes more organized. We have a negative value here. Now, you're subtracting a negative value. So this overall term ends up being positive. That works against it being spontaneous. So if you have a decrease in disorder like you have here, when is that going to occur? That's going to occur when you have a really low temperature. So a low temperature will keep this term low. So we'll say spontaneous at low temperatures. And of course, low temperature, that's a relative term, right? Low temperature versus high temperature. And looking at our last scenario, here you have something that's endothermic, meaning you have to put heat in. So that's not a great factor if we want a reaction to occur. However, it is increasing in disorder. So this term overall ends up being negative. That's great. So as long as this term is bigger than this one, you'll get a spontaneous reaction. Well, when is this term going to be bigger than this one? Well, when you're at high temperatures. So we're going to say spontaneous at high temperatures. Alrighty, I hope that helped organize stuff for you. So a couple of things that I just want to summarize with. When is a reaction most likely to occur? When it's exothermic, means heat energy is being given off, and when it's becoming more disorganized. All right, we're going to send it back over to the desk. Take it away, Kevin. Okay, so what we're going to do now is we're going to take a look at some thermodynamic data. So if you notice in the materials section in the folder for this unit, I've actually posted something called thermodynamic data. And if you open it up, you're quite surprised. There's a lot of numbers in there and absolutely no explanation. So what we're going to do now is we are going to send it out to our resident expert, Kevin, who is going to explain the meaning of the three columns, so delta H, delta G, and delta S, and how to use those when we're actually doing chemical reactions and equations. And then finally, we'll finish up today by taking a look at a homework problem, and that should sum it up. All right, so without further ado, I'm going to send it over to our expert, Kevin, who's going to explain what is meant by all those numbers in the chart. Take it away, Kevin. All right, thanks for joining me over at the big board. So if you were to open up the document, and again, this document is available up on Schoology in the materials folder, it is pages and pages long of all of these different constants that you see behind me. So I just want to take a few minutes and go through the meaning of all of these up here and explain to you why some of them are zero, why some of them are negative, and all of that. All right, so today there's a red box around the delta H because that's what we're going to focus on. If you notice, I've been using the term delta H of reaction, but this has a little delta HF, and that delta HF means delta H of formation. So it's the heat energy that is either absorbed or released when this compound forms. So if you look over here, I don't know how these weather people do this. If you look over here, we're going to start off with aluminum. So if you notice, the delta H value for aluminum is 0. Now, think about this for a second. Aluminum is an element in its natural state. It doesn't need to form. So the energy associated with its formation is 0. You'll notice barium, also 0, and beryllium is also 0. So for the most part, elements found in their natural state are going to have a value of 0. Now, I don't know if I could, no, it won't let me, but if you go down and you look at bromine, which is right over here, down there, you'll see Br2 as a liquid, 0. Br2 as something else, a gas, non-zero, because that's not its natural state. So its natural state is room temperature to be a liquid. And if you notice up here, a couple of constants, so you'll notice that all of these values are taken at 25 degrees Celsius. Yes, it's hard to believe, but all of these constants would have different numbers associated with them if we were at a different temperature. So next part, going over to the second column, we have delta G of formation. So the spontaneity of it, again, the value for any element in its natural state is going to be 0 because it doesn't need to form, that's its natural state. And then finally, there is a measure of disorder. Now, every substance has a measure of disorder except for one, and if you look through the entire chart, you'll see it's the hydrogen ion. So basically what they did was they measured how messed up everything is with this baseline. So we're going to start with a single proton, a hydrogen ion, and we're going to measure everything against that and assign it a number. So every value has a number, and its number is based on how disorganized it is compared to a single proton. So if you notice, you have an element like aluminum, it has a certain value, and then if you go into a compound like aluminum chloride, it's more disordered, so that has a certain value. And then you'll notice aluminum oxide, that has a lower value. That's probably because a lot of aluminum exists as aluminum oxide, so it's slightly less disordered. Okay, last part. So when we actually go through, and Kevin's going to explain this in a second, and do these equations, for today, we're only going to be pulling numbers from this first column. So all of the numbers that I'm talking about today are going to come from the delta H of formation column. And then after that, we'll get into the delta H of reaction, or delta G rather of formation S, and then the delta H of reaction. All right, so hopefully that made sense. Don't be overwhelmed by the amount of values. Look very closely. Sometimes you're going to see 2 or 3 examples of a single substance, and the only difference is they're going to be at a different state of matter, so a solid, a liquid, or a gas. So just pay attention closely. Most of the time when students make errors on this, it's because they did not choose the right state of matter, not that they chose the wrong compound. All right, I'm going to send it back over to Kevin at the desk, who is going to send it off to Kevin again for the actual example problem. All right, take it away. So in our final segment, we're going to take a look at an example problem, and then you've probably already figured out that you have 3 homework problems to try this out on. As always, we're going to send it over to Kevin with an example problem for us to take a look at. Kevin? All right, thanks, Kevin. We're going to look at one example problem to finish up today's class, and the example problem that I chose was the combustion of methane. So if you notice, we have methane, CH4, reacting with oxygen, producing carbon dioxide and water. Notice that it is extremely important that you are aware of what states of matter you're dealing with, because some of the values, when you look them up in the table, will have different numbers depending on whether you see that as a gas or a liquid or whatever the case might be, even a solid versus an aqueous solution of something. So I'm going to begin by writing in my coefficients for the balanced equation. So I have 4 hydrogen, so I'm going to put a 2 in front of the water here. I have 2 oxygen, 2 times 4 oxygen here, so these end up both being 1s. Now, I know some of you are probably intimidated by that equation that's sitting at the top there, so I just want to go through and explain that to you. When you're calculating the enthalpy of a reaction, the heat energy associated with a reaction, you have enthalpy of a reaction. This means at standard conditions, so 25 degrees Celsius or 298 Kelvin. It is equal to sigma, the sum of the delta H of formation at standard condition for the products minus the sum of the delta H of formation values, the values in the table, at standard condition for the reactants. The most important thing that you can take away from this entire thing up here is that you look at products first. So you're actually going to do the product side first, and then you're going to subtract from that the reactant side. So it's almost like final minus initial. All right, so when you're setting this up, I'm going to start all the way on the left here because these tend to be kind of long. So I have delta H for the reaction at standard conditions is equal to. Now, one of the things that I like to do to keep myself organized is to use giant square brackets to enclose the products and then the reactants. That way I know where my values are in case I made a mistake and I need to go back and fix something. So I'm going to start off by putting a giant square bracket here, and then I'm going to look up the value for carbon dioxide. So if you look up the value for carbon dioxide, it's not actually far away from where methane is located under the carbon compounds. You find out that the value for carbon dioxide is negative 393.5 kilojoules per mole. Now, what you need to do is you need to take each value, once you get it, and multiply it by its coefficient from the balanced equation. Now, in this case, it's just a 1, so it's not going to really change anything mathematically, but it helps with the bookkeeping, and if we make a mistake, it helps us we try and go back and figure out what went wrong. So the next part I'm going to do is I'm going to look up the value for water. So I use regular parentheses to enclose each value and then square brackets to enclose products and reactants. So when you're looking up the value for water, 2 things. Number 1, they organize water in the table with oxygen compounds. That's probably because the central atom in water is an oxygen atom. So when you're looking up water, you're going to look under oxygen, and I also want you to pay attention because there are 2 values for water. There's water as a liquid and water as a gas. So since we're doing a combustion reaction, we're actually going to look at the value for water as a gas, and that value turns out to be negative 241.82 kilojoules per mole. So I'm going to close that bracket. Again, you want to multiply that by its coefficient from the balanced equation. So that time we're going to write in a 2 there. And now I'm going to close my bracket because I'm done with the product side. If I had 3 products, then I would have 3 different things in here. If I had just 1 product, then I would have just 1 thing in here. So the number of products that you have should match the number of numbers here. Same thing up here. So now we're going to take a look at the reactant. So I'm going to go subtract, because we're subtracting here. Now I'm going to open another square bracket. This time we're going to look at the reactant side. So the value for methane, when you look up methane in the table, it has a value of negative 74.8 kilojoules per mole. Close that bracket. Multiply it by its coefficient from the balanced equation, which is just 1. Now I'm going to look up the value for oxygen. Remember, within the square brackets, things get added together because it's the sum of the products. That means add them together. It's the sum of the reactants. Add them together. The two things, products minus reactants, get subtracted from each other, so that's where that is coming from. So if I look up the value for oxygen, you won't be surprised if you watch the whole video to learn that the value for oxygen is 0 because it's an element in its natural state. So we're going to find 0 kilojoules per mole here. We can go ahead and multiply that by 2, but it's really not going to matter since that part is a 0. And finally, I'm going to close my square bracket. Sometimes what I like to do just to eliminate some of the confusion is if I have something that's 0, I just draw a line through it like this to remind myself that I don't have to worry about that. So when I'm typing this into the calculator, that's not going to be relevant to me. All right, so in the next part, I type this into the calculator. So I have delta H for a reaction is equal to, so the left side of this, the product side of this, turns out to be negative 877.14 kilojoules per mole. Keep that in the square brackets. And on the reactant side, of course, we just have that one number multiplied by 1, so that's negative 74.8 kilojoules per mole. Another common mistake is when students forget that we have a double negative going on here. So we're subtracting a negative, so we're actually adding it. So our final answer for the delta H for this reaction is equal to negative 802, I guess I don't need the square bracket here, negative 802.34 kilojoules per mole. So here is my final answer. These problems are not difficult. The most challenging part of the problem is making sure that you are able to correctly identify what the material is and its correct state of matter. So with that, I'm going to send it back over to the desk for Kevin. He's going to close it out for today. I hope everyone has a great weekend. Again, Zoom session at 10 a.m. and 12 p.m. And if you have any other questions and you can't visit during those times, please send me a message through Schoology or through email. I hope everyone has a great weekend. Thanks, Kevin. And that will do it for today. So your homework assignment tonight is to complete problems 1, 2, and 3 in the enthalpy practice problems assignment. Please make sure to scan that as a PDF and submit it using the Dropbox that I posted on Schoology. If you have any questions, please reach out through either Schoology Messenger, email, or better yet, stop by on my Zoom sessions at 10 and 12 p.m. 10 a.m. and 12 p.m. 10 p.m. I will be sleeping, so don't bother. All right, that does it. If I don't see any of you at the Zoom sessions, have a great weekend. I look forward to next week and continuing with thermochemistry. Thanks a lot, everyone. Have a great weekend.